On a sunny day in 1950, physicist Enrico Fermi famously asked a simple yet profound question. Where are they? They, of course, meant extraterrestrials, the aliens that, by all logic, should exist in a universe as vast as ours. The Fermi Paradox refers to this puzzling contradiction between the high probability that intelligent life should be out there and the complete lack of evidence for it. Space is unimaginably immense, with hundreds of billions of stars in our galaxy alone, many of them harboring planets. By the numbers, one would expect intelligent civilizations capable of technology like radio or spacecraft to speckle the distant stars, as Fermi mused. Yet the skies remain eerily silent. No undeniable signals, no visits, no signs of cosmic neighbors. Decades of searching have yielded nothing but silence. We find ourselves asking again and again, where is everybody? Scientists have grappled with this paradox for years. Early on, astronomer Frank Drake formulated an equation to estimate the number of detectable civilizations, multiplying factors like star formation rates and probabilities of life. Depending on optimistic or pessimistic inputs, the Drake equation can predict a galaxy teeming with civilizations, or virtually none at all. The truth is, each factor in that equation, from the fraction of stars with habitable planets to the lifespan of technological societies, is hugely uncertain. Still, given the sheer multitude of stars and planets, many experts expected the cosmos to be bursting with life and intelligence. The absence of any contact or evidence is therefore deeply perplexing. Over the years, numerous hypotheses have been proposed to resolve the Fermi paradox. Perhaps interstellar travel is too difficult, or aliens are rare. Maybe they exist, but choose not to communicate. Maybe civilizations self-destruct quickly, or maybe life itself is incredibly scarce. Each idea offers a possible answer, yet none is proven. Among these explanations, one has captured both scientific and popular imagination for its sweeping implications: the Great Filter. The Great Filter is an idea first articulated by economist Robin Hanson in the late 90s. It's not a physical filter, but a metaphor for a critical barrier or bottleneck in the progression of life. Simply stated, the Great Filter hypothesis says that between the origin of life and its potential future among the stars, there must be at least one extremely improbable step or obstacle that almost no civilization manages to overcome. In other words, while there may be many hurdles on the road from microbes to an interstellar species, at least one of those hurdles is so exceptionally difficult that it stops nearly all attempts at reaching advanced spacefaring civilization. This would explain why the universe seems empty. The vast majority of life never makes it past that roadblock. Hansen described the situation like this: any given chunk of dead matter, like a planet, has an astronomically low chance of ever giving rise to an expanding, lasting life civilization. Somewhere between lifeless atoms and galaxy-spanning super civilizations, there is a barrier that almost always prevents the latter from happening. Humanity naturally wants to know, how far along this filter are we? Have we already passed the hardest part, or is the worst still to come? The answer carries profound consequences for our future. It's important to note the Great Filter is not assumed to be a single identifiable event, like a specific catastrophe or invention necessarily. It's more about the aggregate probability of a series of necessary steps. The term filter suggests something actively filtering out civilizations, but in reality it might simply be the cumulative effect of natural difficulties. It's a way of reframing all the required steps for life to reach our level and beyond in terms of probability. If you list all the key milestones that must happen for a species to become spacefaring, and then imagine one of those milestones is nearly impossible, that would serve as the Great Filter in practice. So what are those key steps? We can outline the many hurdles from microbes to galaxy-wide civilization, and consider where the filter might be hiding. Robin Hanson and others have proposed a sequence of critical milestones. For example, Habitable world formation. First, a star system must form a planet in the right zone. A habitable zone where liquid water can exist and where conditions are stable enough for life. Not every star has planets, and not every planet is clement. This is a prerequisite, though planets like Earth now seem common in the galaxy. Abiogenesis. Life itself must arise from non-living matter. This is the process of abiogenesis, where chemistry crosses the threshold into biology. Somehow, simple molecules must self-assemble into a self-replicating system, the first cells or proto-organisms. We do not yet know how easily or rarely this happens. Reproduction and genetic machinery. Those early life forms must develop the ability to reliably reproduce and pass on information, likely via molecules like DNA or RNA. Without robust heredity and mutation, life cannot diversify and improve. The emergence of genetic code and complex biochemistry is a hurdle in itself. Complex cells. Simple single-celled organisms, like bacteria, must evolve into more complex cells with a nucleus and specialized structures. On Earth, this happened when primitive cells merged to form eukaryotic cells. This step only happened once. All complex life shares that ancestral event, suggesting it might be a rare fluke. Multicellular life. Single cells must learn to cooperate as one organism, the evolution of multicellular life. This allows the existence of plants and animals with differentiated tissues. On Earth, it took over 3 billion years of mostly single-celled life before multicellular creatures became common. Intelligence and tool use. Among multicellular organisms, eventually a species must develop intelligence, technology, and tool use. This includes not just brain power, but things like dexterous appendages or other means to manipulate the environment. Many forms of life are intelligent in various ways, but only one lineage, humans, produced advanced technology on our planet. Advanced technology. The intelligent beings must go on to invent advanced technologies, things like industrialization, complex machines, radio communication, rocketry. Reaching a level capable of interstellar communication or travel is a huge leap. Human civilization is somewhere around this stage now, with radio telescopes scanning the sky and probes leaving the solar system. Space colonization. Finally, a technological species must actually expand beyond its home world, colonizing other planets or star systems. And crucially, they must do so without destroying themselves in the process. This might involve overcoming long-term risks and ensuring survival across many generations. That's an arduous gauntlet of steps. The Great Filter hypothesis holds that at least one of these steps is so improbable that it effectively filters out almost all civilizations from ever getting all the way through. If, say, the origin of life is almost miraculously rare, then very few planets ever get past step 2, which would explain why we don't see aliens. Alternatively, if becoming multicellular or intelligent is the truly rare event, that could be the filter. Or it could be that many civilizations rise to technology, but almost invariably self-destruct before colonizing the stars. In that case, the filter is at the end of the chain, catching civilizations right when they reach for the cosmos. It's sobering to think that 99.999% or more of fledgling life forms might fail at one of these hurdles. But that grim outcome for others would nicely solve our paradox. The universe appears empty because, at almost every turn, it is empty of peers. They never made it this far. One of the most hopeful possibilities is that the Great Filter is already behind us. In this scenario, the hardest, unlikeliest steps have already happened sometime in Earth's past. That would mean humanity, or life on Earth in general, has done what almost no one else in the universe managed to do. We've passed the big test. Our apparent aloneness would then be a good sign. It indicates we're past the cosmic bottleneck, survivals of a trial that most worlds never overcome. Strange as it sounds, the silence of the skies could be reassuring if it means we're on the other side of the filter, destined for a long and adventurous future among the stars. If the filter is behind us, what was it? Candidates include some of the steps we just outlined, likely one of the earlier midway ones. Let's explore a few leading ideas. Rare Earth conditions. Perhaps intelligent life is extremely uncommon because the right conditions rarely all coincide on one planet. This is known as the Rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee. They argue that Earth benefited from an exceptional set of circumstances that might hardly ever occur together elsewhere. For instance, we orbit a stable, long-lived star that isn't too large, huge stars die quickly, and not too small. Small stars can tidally lock planets or emit flares. We're at the right distance for liquid water and not too close to the galactic center where deadly radiation is high. Our planet has a large moon stabilizing our axial tilt and thus climate seasons. And we have giant planets like Jupiter in our solar system that help divert dangerous comets, acting as a cosmic shield for Earth. Earth's mass is sufficient to hold an atmosphere and oceans. We have a molten iron core generating a magnetic field to protect the surface from harsh solar winds. Plate tectonics recycle nutrients and regulate the climate over eons. Even the timing of events in Earth's history, like the rise of oxygen in the atmosphere, lined up just right for complex life. In the rare Earth view, complex life, animals and higher forms, may be extraordinarily rare, even if simple microbial life is common. Ward and Brownlee point out that bacteria appeared on Earth very early and survive almost everywhere, but more complex multicellular life seems to require a far narrower set of conditions and took much longer to establish. So the Great Filter might be passing from simple life to complex life, a transition that Earth managed by a fortuitous mix of factors that almost never align elsewhere. It's worth noting that Rare Earth is a hypothesis under debate. Many of the specific critical factors it identifies have been questioned by other scientists. For example, some research suggests having a Jupiter-sized neighbor could actually increase impacts in inner planets rather than reduce them. And we don't know yet how truly rare plate tectonics or large moons are in the universe. The Rare Earth proponents welcome these challenges. Their intent was to spur deeper investigation into all subtle things that made Earth what it is. Proven or not, the Rare Earth idea does highlight just how many things had to go right on our planet for us to be here. If that combination is 1 in a billion, that could very well be the Great Filter, meaning we are essentially lottery winners on a cosmic scale. Abiogenesis is extremely rare. Another possibility is that the origin of life itself, the step from chemistry to the first simple cells, is the nearly impossible hurdle. Perhaps abiogenesis happens only once in a blue moon, even on habitable worlds. After all, despite tremendous advances in biology, we still don't know exactly how life began on Earth. If it requires an extraordinarily precise sequence of events or rare conditions, like a very specific primordial soup, lightning strikes, deep sea vents, etc., it might seldom occur. Some scientists consider abiogenesis the leading Great Filter candidate, as it's arguably the least understood and potentially lowest probability step. Supporting this, we have observed no independent genesis of life anywhere else yet, not on other planets or even a separate second genesis on Earth. If life were easy to start, we might expect it to have arisen multiple times in different settings. Instead, all known life shares a single origin. It could be that many Earth-like planets out there never sparked life at all, remaining sterile despite favorable climates. Interestingly, life on Earth seems to have appeared relatively quickly once the planet became habitable. Earth formed about 4.5 billion years ago, and by around 4 to 3.8 billion years ago, almost as soon as the heavy bombardment phase ended and stable oceans existed, we see evidence that microbial life was present. Some take this to mean abiogenesis might not be so improbable after all. Maybe life emerges readily given the right conditions. However, we must be cautious. We only have one data point, Earth. And naturally, life had to arise here at some point for us to exist and observe it. Even if the odds were very low, we wouldn't be here to notice unless we happened to be on the lucky world where it did occur. In other words, even a universe where abiogenesis is extremely rare would still have one planet, ours, where it happened early, because only on that kind of planet could observers evolve to marvel at it. This is a form of the anthropic principle. We might falsely perceive life's origin as easy because we don't get to see the countless dead worlds where it never happened. So, the quick start of life on Earth isn't a definitive argument. Abiogenesis could still be the great filter, hiding behind a deceptive veil of anthropic selection. The jump to complex cells. Let's say simple life, like bacteria, does commonly start on many worlds. The next big leap on Earth was the evolution of the eukaryotic cell. Larger, complex cells with nuclei and organelles, small specialized structures. This seems to have occurred only once about 2 billion years ago via an unlikely endosymbiosis event, where one microbe engulfs another and forms a permanent cooperative relationship. Some biologists, like the late Lynn Margulis, have suggested this was an extraordinarily improbable happenstance. If so, most planets with life might remain stuck at the microbial stage indefinitely. Oceans full of bacteria and algae, perhaps, but nothing like animals or intelligent beings. In the context of the Great Filter, the eukaryote transition could be the filter. Earth got incredibly lucky that day when two cells merged to become more than the sum of their parts. Without that event, you don't get multicellular organisms complex enough to build technologies. This idea aligns with the thought that maybe the universe is teeming with bacteria, but bacteria doesn't build starships. In other words, life might be everywhere, but intelligent life could still be effectively nowhere if the intermediate steps seldom occur. Evolution of intelligence. Even after complex multicellular life emerged, around 600 million years ago in Earth's case, the rise of a species with human-level intelligence was not guaranteed. It took a series of contingent events, evolution experimenting with different body plans, one lineage, primates, developing large brains and dexterous hands, etc. It's possible that intelligent, tool-using life is extremely rare in the cosmos. On Earth, there have been millions of species, but only one, ours, that developed advanced technology. Some scientists argue that if you reran Earth's tape of life, the chance of getting a technological species is not high. Others point to certain evolutionary advantages of intelligence, problem solving, adaptability, and suggest it might eventually arise in many biospheres in some form. The truth is, we don't really know how inevitable or fluky the emergence of an intelligent, technologically capable species is. If it's a 1 in a billion outcome, even on planets with complex life, that would be an effective great filter. Perhaps many planets have lush ecosystems with animals and rich biospheres, but no species ever invents radio transmitters or rockets. From our perspective, such worlds would still be silent. We wouldn't detect any technological signals from them, and they'd never reach out across space. Each of these possibilities, and they aren't mutually exclusive, paints a picture of a universe where life or intelligence is a rare jewel. If any one of these steps is astronomically unlikely, it's enough to explain the Fermi Paradox. We could truly be alone, or one of so few that the nearest peers might be galaxies away. This outlook is humbling. It suggests that our existence is an incredibly lucky break. As unsettling as that might feel, it also implies the cosmos holds vast open potential for us. If no one else is around, then we might be the ones destined to spread life's light further. As the Astronomy magazine put it, if the great filter is behind us, the universe may be ours for the taking. That could be a hopeful interpretation. We're the early bird, perhaps the first to rise to intelligence in our galaxy. Somebody has to be first, after all. However, this hopeful scenario comes with a poignant catch. If we really are the only or first technological civilization, the responsibility on our shoulders is immense. There are no other voices to join a galactic conversation, no ancient mentors to guide us. It's just us. In a vast silent universe, the survival of our civilization, and the life it carries, becomes a matter of cosmic significance. We would bear the duty to safeguard this rare spark and possibly to seed life elsewhere. This realization can be both inspiring and sobering. In part 2, we'll explore the uncomfortable idea that the Great Filter is still ahead of us. Like and subscribe to be notified.